single discussion. That's it. In short, some geeky topic conducted by a geeky person where the geek people discuss on that. That's it. And today we have Deepak Chirammel. So he's gonna present a topic. So have fun. Thank you.
Hello, everyone. Good evening, and thanks for joining the session. Uh, just a quick check. Anyone working in language models, AI, this kind of domains? Just trying to understand the audience. Okay. Anyone working? Okay. Good. The chatbots? Just asking. All right. Uh, and what about others? You are new to AI or language models? Any college grads here? Okay. I think. All right. So today's session is going to be language models. We'll talk about what is language modeling. We'll start with some basics because we are going to go for a like fine tuning approach called LoRA. But to reach there, we just need to have some basics. So again, like the usual audience I get is mostly college students. So I'm trying to make it into very basics as well, but it will not be that much depth. I'll try to cover whatever I could and try not to avoid any jargons. All these parts I'll try to do. But yeah, have fun. Right. So yeah, about me, I'm Deepak. I've been working with Thoughtworks for almost like 6 years now. Prior to that, also I used to work in another product company. In total like 12 years. I'm doing in my capacity of like a lead consultant here. Yeah, a core geek has think yeah a core geek. If you let me, if you know me, right. Okay. Anyone from Zoom? Can you tell like is it audible now? It's audible. Okay.
Yeah, it's audible now.
All right. Thanks for confirming. So let me move on. So quick disclaimer, what we are going to learn about session. The session is basically to understand about language models in a nutshell. It's actually a part of natural language processing. We'll talk about what these are and all. We'll start with what is the initial language models that we had in the earlier days. That is about like statistical models or probabilistic models. And then we'll actually go to the recent modern language models like transformers, GPTs and all. Again, transformers and GPTs goes hand in hand. We'll talk about GPTs a lot because we are going to fine tune a GPT at the end. Right. Again, the intention is to gain breadth from the session, not like the depth part. Again, depth we cannot cover in 1 hour session. That's the truth. But we are open for any suggestions and we'll take any feedbacks so that it is better in the next set of sessions as well. But do let me know how the session is for you. Like how is the session overall at the end. Right. At the end of the session, like what I wanted to do is like everyone should be able to like at least have some confidence to build some language models, especially like at least small language models, not the large language ones. SLMs, we can try to give it a shot. Again, have that confidence at the end of the session. That's the intention of this session. Again, this session will not cover too much depth, but again, that is up to you to figure out how much depth you want to go. Yeah, and definitely not production grade. That is not going to achieve in 1 hour. So I'll try to cover some mathematics concept, but again, not go into deep what is that happening, but you will get an overall idea. But you are feel free to interrupt me if you are not getting the clear picture. I'll try to stop. But if the discussions are going on for a lengthy time, we'll try to pause and then back on track. We will try to cover the sessions and we'll try to answer the questions at the end. All good? Okay. So the agenda for today's session is like, as I said, like first we'll talk about what is language model, what is the history of language model, where it started, and where are we currently. We'll talk about the historical evolution over the time. Again, we are talking about a time period of like 30, 35 years, not 35, I think 1950 onwards, there are initiatives on language models. So we'll give you a historical evolution where we started and where we are currently. Again, the initial language models that we can find in the starting point, I think in 1990s is actually Ngram models. That is the classical probabilistic language models. We'll have a showcase of what is a Ngram model and how it is able to generate a new data. All these things we'll try with a hands-on demo. Then moving forward, fast forward, we'll try to talk about transformers. Again, transformers are actually it's almost an 7 years, 8 years old technology. But again, that is actually evolving on a day-to-day basis. A lot of research going on. Again, all the GPTs or the Gen AI that you're talking about, the fundamental is a transformer. So we'll talk about the evolution of GPTs over time. Again, anyone tried the latest GPT-5? I think it was released last 2 weeks back. Anyone tried it out? Okay. Okay, it's there in preview. How is this? How is the GPT-5 feedbacks? Okay, others? It's a mixed opinion, but that's why I'm asking. Okay. Okay. Anyone know what is the parameter size like? We talk about like 7 billion parameter, 20 billion parameter model. Curious, anyone want to know? Actually, OpenAI did not disclose it. I just wonder, it's a tricky question. Okay, so we'll talk about GPTs, the evolution of GPTs over time. And again, all GPTs, the first and foremost thing is called tokenizers. So we'll talk about tokenization strategies that these GPTs use in their system. And we'll talk about like techniques like PEFT, that is a parameter efficient fine-tuning technique. So again, we'll talk about a very specific fine-tuning technique called LoRA in depth. We'll have a demo, but we will not be able to run and train it. Again, it requires like huge compute resource, but the walkthrough of the code will give you an understanding what is LoRA and how to do a fine tuning of a large language model. With that, we will end the session and we'll be open for any questions. That's the agenda for the session today. Okay, so moving on to what's a language model in anyone's term. It's just a probabilistic model. It is generating something based on probability, generating next word. Like the latest Gen AI, it actually takes next word. What is the probabilistic next word? And then it keeps on going. And these are called autoregressive models. We'll talk about that. But what it does is, if you give a set of tokens, it actually gives you a probability distribution. What is the next token going to be? In a simple shell, that is what a language model is. Now, there are concepts like tokens. We'll talk about what is tokenization and all in depth. Again, these are the foundations of search and agents in language, in LLM world. Again, the initial use cases was very different. We were using it for prediction, classification. Okay, is the text a good, basically for ratings. Is it a good review? Is it a bad review? Those kind of classifications was used. But nowadays, everyone is using it for prediction, or also called as generation, generating new text. But yeah, in this session also, we'll be talking about generation models a lot. In generation is what we are interested in also in this session. Right. So when you talk about Gen AI is something like you give it some prompt, it gives you the next word. Okay. As I told before, any language model, it is giving you a probability distribution. For example, I prompted like deep learning is very. Then it actually tries to check, okay, what is the next probable word that will come. And it will have a probability distribution. For example, 43% says it is a powerful. Again, there is decoding algorithms. If you ask it to make it creative answer, it might actually choose a very random some numbers. But if you wanted to give it like very specific answer, think clearly and specific only, that it will give you the highest probability. So that is typically GPTs or Gen AI. That's what currently doing. And it is actually doing in a regressive fashion. Regressive fashion means once it generates the next word, it again goes back and goes to the next word, keeps on generating it over and over again until it reaches some criteria. And these GPTs are called auto-regressive models. For example, I'm just giving an example. So I give deep to an LLM. It is deep learning. Now, once it have deep and learning generated, it will actually try to find the next word, is, then is very, and then powerful. So it keeps on generating. I think all of you might have tried this. Maybe I can give a quick demo how ChatGPT does this. So what it is doing is, it is getting the context, it is trying to understand that context and trying to generate a next set of words. That's what typically, so you can see it is generating one after the other, and it is actually continuing this. And all of this generation usually happens, I think, okay. So all of this happens in a like regressive fashion. So that's why all these GPT models are called autoregressive models. Getting the point, right? What is autoregressive? Again, it's not a jargon, it's actually a term which is used. True. Okay, what's the full form of GPT? Anyone? Transformer. So basically it's a transformer. So historical evolution of language models started I would say like just for time's sake, we'll start it for 1990. I have a next slide which actually talks about even 1950s. So in the 1990s, the first statistical language model was created. It's using a technology called n-grams. You can hear me, right? N-grams. So post that during the 2000 range, we actually got something like neural language models. It's actually using neural nets called perceptrons. Then comes like again 2010 ranges. There is a large scale embeddings. Embeddings called as vectorization. So again, Stanford was in the word to work is actually a contribution from Google, which actually tries to vectorize each word. Again, using this vector embeddings, they are able to generate using next set of words. There are actually short-term language models which came into the picture, like RNN, recurrent neural network, long short-term memory, all this during this 2010-2015 range. Again, in 2015 is the main point. It's a pivoting point where there was an interesting concept called attention mechanism. And attention mechanism which led to the creation of first transformers in 1970. I'll talk about the papers that are created. And from 2017 onwards, it's always been transformers. I think the first transformer, after the transformer, the first GPT came into the picture in 2018. But again, the chat GPT that is officially known, it got a UI interface in 2022. I think that was the moment where it was widely adopted. I think, yeah, fast forward, you know the current situation. I think we are in GPT-5, which was released 2 weeks back. Right. Before 1990s also, there was concepts like there was attempts to create language models. Again, ELISA was the first language, I would say the very first, which is at least known in the current industry. ELISA, any idea what this language model is underlying doing? Anyone heard the term ELISA?
It was
ELISA
like a
basically
first
rule-based.
chatbot kind of.
Yeah, this was the first chatbot which was able to clear the Turing test. Yes, that's true. But how it did? It is actually doing simple rule-based and pattern matching. You ask any questions, it actually answers what it knows. If it does not know, there is a standard default responses. It will fall back to those responses. But again, the interesting fact is ELISA was able to actually overcome the Turing test and confuse that whether it's a bot or a human. So that was the initial initiatives in language model. Again, fast forward, we have 2010, I actually talked about like vector embeddings. Again, 2011, we have Google Brain. That was a lab of Google, which came into the picture. It was a long-term initiative to build this kind of AI initiative under Google. And in 2017 is the first transformer architecture that came into the picture. Yeah, ever since I think I already explained on the previous slide. So, right, we'll talk a little bit more on the earlier phases, which is classical n-grams model. I think I talked about here. So n-grams was the first statistical language model. What is n-grams? Yeah, n-grams is nothing but a prediction model. Once it has the set of vocabulary or data, it tries to predict. If you give it a prompt, it tries to predict based on that prompt what is the next word. Again, this is actually just based on counts, like word count or like patterns, stuff like that. I'll talk about, I'll show a quick demo. Okay, so if you wanted to explore n-grams and the initial statistical language models, NLTK is the best tool that we can get out. So I import an NLTK and I am actually uploading a data set. I'll open the data set firstly. So this is a simple review data set. A review data set means like whoever has gone to some restaurants and then given review. Okay, which food I like? I love these cookies. Again, they have given some reviews on the food over the years. I think this is a data set of around 1,400, 1,500 kinds of data. Okay. Now, using this data set, I wanted to create a statistical language model using n-grams. That's the intention. Everyone clear with what I'm trying to do here? So going back, what I'm doing is using this data set, I am uploading it and just doing some reading. What is this data set? I'm just printing the head of this data frame. Then using pre-processing, and I'm just confirming everything is a number, text, and everything. Then what I'm doing is, once I process this text, I am actually converting each of these words into individual words, sentences split into individual words. So the process text will give you something like individual words of that sentence. Okay. Now, a trigram model means, what trigram model means is, it will take, for example, I am going to. I'm just giving a sentence, I'm going to. It is actually trying to predict the next word based on the current word. So if it's a trigram word, it will try n-2. That is 2 words before that, and then try to figure out what is, based on these 2 contexts, what would be the next word. Again, it's a statistical, it's a count-based mechanism. So once I load the model, and then I am trying to recommend words, this is a function, it will recommend at least 3 words. What is the next 3 words? Again, in sorted order. So if you want to try, for example, I am giving it a test sentence. I love these cookies. I'm on a paleo diet right now, and these cookies. What is the next word? If I try to run, it is actually predicting, okay, the next words could be R, I, or close. But how it is predicting? It's predicting based on the vocabulary. So based on these last two words, it's a trigram model. Trigram model means it is n is 3, and so it is taking n-2 characters. These cookies, whenever in these cookies came in the vocabulary, what is the next probable word? And it is taking the statistically, which is, or probabilistically, which is the next most popular word. So it is giving something like R. I can give another test sentence. I really enjoyed eating this. So it is, the moment I type something like I enjoyed eating, it is trying to generate the next word. In the next word in order based on the vocabulary that we have, right? It is actually trying to generate, okay, it's a brand. It could be a brand. Next word could be a brand. Then, okay, if I take brand as an example, I can even get the next word after that. You get the point, right? How the initial language models and all work. Clear? So far, what is the initial statistics model? What is n-grams? Okay. Go back to the deck. So these are the initial statistics models or language models that was existing in 1990s during that time frame. Yeah, it uses n-1 characters. For example, if I'm using n is equal to 3, then it's actually taking the last two characters and then trying to predict this 2. To some extent, it was actually better because it is able to distinguish. It is actually trying to rate last 2 characters, n-1 characters and n-1 words, and from there it is trying to predict. So some amount of context is getting preserved. So if I try to give a bigger n, for example, I try to give it n is equal to 5. Then I am actually trying to take four letters before I predict something new. Right. Again, there are advantages of this kind of probabilistic models. But there are also, again, in 1990, what we are talking about is there are actually a lot of challenges. For example, we do not have a huge data set. Currently, what we are talking about is petabytes or terabytes of data. We did not have that kind of data sets in 1990s. And again, there was actually a limitation on hardware. We did not have the memory cost. Again, that is one of the reasons probably n-gram models or the probabilistic models did not come to the limelight a lot. Again, there are limitations also. The more size we increase, for example, n is equal to 10, we can only give it like n is equal to 10 or something. The computations becomes more and more difficult. And that's why will have always a limited long-range context. That is the challenge. But the advantage is it is actually able to create a fast baseline. You can create a base model very fast. You don't need to train it, like, for example, on GPUs or like for months or days, something like that. Right. Some things that we need to worry about is, again, these are probabilistic model. So if it is not able to find some particular words, there is always going to be challenges like zero probabilities. So we need to avoid that. There is a technique called smoothing. Again, I'm not going to deeper. Again, that will take more time. So there are smoothing essentials that we need to consider when you are thinking about like probabilistic models. Clear so far? Right. Ever since the probabilistic models came, again, what could be the next big thing that was being researched, and eventually the language neural net came up. Again, neural nets are actually you convert a text into some numbers, and these numbers can be multiplied with some weights. And that weights, if you try to put it through some activation layers, it will try to generate some number which can be decoded as a word. In what should be the weight and all, when neural nets come into the picture, this kind of architecture was more evident. And this was actually very good in the 2000 ranges. Neural net is still used to some extent, but again in a different format. But neural nets are the backbone of even GPTs. Okay, so a typical neural net will have something called weights and bias. Again, any idea what is weights and bias used in GPTs? That is internally called as the parameters. When you call 7 billion parameter model or 20 billion parameter model, each parameter is something like of a weight. Weight plus bias is a parameter. Okay, but so we are not using neural nets directly, but we are using something different in transformers. But the basic fundamental principle came from neural nets, even the latest one. Again, the advantage of neural net is it will be able to generalize things well. Like in the previous one, we have to go for probabilistic, and if based on the quality of data, the probability can go down, go up. Again, what are we asking about? But the advantage of neural net is even if it is unseen data, it will be able to generalize something. Something means it not wrong answers or answering the answer. At least some decent answers it was able to generate. And again, we were able to generate it for huge data sets. That's why neural nets are actually better than probabilistic models. Okay, there are a lot of neural network-based language models in that picture. For example, RNN. RNN was the actually go-to default. Anyone knows what's the use case of RNN? Quick quiz. At least who are there in early Google search and all, you might have seen. The moment you type something in Google search, it actually tries to find the next word. Might have seen, go to google.com. Autocomplete, correct. Autocomplete, I'm pretty learning. I'm just typing something. So it is trying to suggest the next word. These and all in the initial days, it was always using RNN, recurrent neural networks. It's able to predict. Nowadays, everything is GPT, but this was actually a very good milestone in those days. Similar to RNN, LSTM was actually a very good useful use case. Whenever you think of like Home Assistant, Google Home Assistant, you are asking it a conversation, it is able to understand that long short memory in the picture. So it's not able to ask, you ask something question and you ask a follow-up question, it does not understand the previous context. It gives you a better experience, right? So LSTM actually fixes those kind of problems like vanishing gradients. So these and all was still very useful. Again, at the current usage also, there are multiple areas where RNN and LSTMs are used. Okay. Fast forward in 2017, we have the first research paper, again from Google, on transformers. The title is the one which is very interesting on this paper. It's called Attention is All You Need. What it mentions is, I'll give an example. I'm giving it a sentence like this. I'm a big fan of Apple. What am I talking about? Is Apple a fruit? Is Apple a company? If I give it something like this. People, are you listening? Are you attending it correctly? It's a company. Why? I did not specify it's a company, but how did you get to know it's a company? Because there are some traits like context. If you read big, I'm a big fan, meaning I'm a user base. It's not talking about a fruit. So if you try to attentively listen for what is said, that is what this paper also talk. The paper actually introduced the term called transformers. And again, the title is actually the attention is all you need to figure out language models. It's a very interesting paper. If you have not read it, this is actually really good. And it also explains, like, if you want to create your own transformer, what it takes to build. They have given a good data set. Again, all of these are from Google Brain, then partnership with like University of Toronto. All this came from Google research primarily. So the main structure of a transformer is right side that you see. It will have two parts. The left part is called an encoder. And the right part is called a decoder. Okay, I'll talk about what is encoder, decoder. We'll deep dive into that. But transformer has two parts. One is an encoder, one is a decoder. So the moment you give it some input. The encoder will try to encode that input, convert it into some numbers, and then it is fed to the decoder. The decoder will try to decode the input received from the encoder, and it will try to generate some output. Once the activation the output is something like softmax or ReLU. These are activation functions. Again, some jargons, don't worry. Some activation function which generates some numbers, which if you try, you can convert it back to next new word. That is the GenAI concept. Okay. But transformers was invented by Google. But how did Google, like, how did ChatGPT come into the picture? Any idea? Okay. Who opens this? OpenAI. Okay. Actually, if you read the fine print, right, the transformer came into the picture for a different purpose. So at that moment, transformers was used for something called translations, like machine translations. So if you go to our Google Translate, right, translate.google.com, I think I have a text here. So this is a text, last session Geeknight. Anyone knows what is the sentence of this one? Spanish, but anyone? Yeah. So it's actually, so if you try to put it in Google, Google Translate, it will tell you. It is what is telling is like it is first able to detect what is the input that is able to. That is the power of transform. Again, to this date, it is still using transformers for machine translation. So whatever text you give, and if you want to transform it into some other language text, so that Google actually used this transformer for that purpose in 2017. But ever since this attention paper came into the picture, there are a lot of. Okay, let me go back to the deck. Ever since this attention paper came into the picture, it actually opened up way forward for different concepts. Okay, attention is the important thing. How can I create attention mathematically or programmatically, and then try to create language models? There were a lot of like a lot of research going on that area. I think this is actually proof. In 2018, 2017 came the first transformer paper. Ever since that, if you see, right, the number of citations which are dealing with transformers actually grow exponentially. Almost close to 20K papers or research papers were created in IEEE during this 2022 period. So transformers are essentially the building blocks for what you see, all these LLMs that you have. But again, transformers are not the LLMs. What is the difference between a transformer and GPT? That's the next part. We'll discuss about that. So transformers came in 2017. Ever since, I think, getting inspiration from those transformers paper came the first GPT. This is also another transformer. Like you understand the full form of GPT, right? It's a generative pre-trained transformer. So it's a form of transformer. What kind of form we'll discuss. Ever since there are a lot of transformers created. BRUT is an encoder-only transformer. GPT-2 came, T5. Then fast forward, there are a lot of competition in the 2024 area. Meta came into the picture. Meta is open sourcing Llama. Then DeepSeek, and the Chinese A lab generated DeepSeek 3. And again, like last 2 weeks before, we got the GPT-5. Right. So all these came from the transformers. But what's the difference between transformer and the GPT? Right. Okay, we'll come to that. So popular GPTs, anyone used all of this or some of this? Which ones do you use? Which is your favorite? Okay. Grok is favorite. GPT is favorite. Okay. Cloud. Okay. Anthropic Cloud. That's good. Uses Gemini. So these are some popular GPTs that are available currently. Again, Cloud is from Anthropic. Grok is from, again, Elon Musk company XAI. Then GPT, as usual, OpenAI. Llama from, again, Meta. Gemini from Google. And DeepSeek from the Chinese AI lab. Right. So I'll come to what it takes to run a GPT. Like if you have a GPT, again, all GPTs has something called parameters. I'm running a 7 billion parameter. I am running a 300 billion parameter. What is parameter? If you understand what is a parameter, it's just weights. It's a neural network concept called weights. it will have something like a multiplication weight matrix plus some bias. That is what is a parameter is about. Now, based on the parameter, each parameter will have at least 4 bytes of data. So if you wanted to run, for example, 8 billion model, so parameter is 8 in billions into 4 times divided by what is the size of each parameter. If it is 16-bit, that means it's 32 by 6. So this is actually a calculation. Again, this is a rough number you need to know because you're going to fine-tune model. You know how much memory you need, because without this, you will not know, okay, can it run on my machine? I only have 1 GB of GPU. So for that picture, I understood. Everyone understood what is the calculation involved on the GPU requirements for like GPTs? Clear, right? Again, GPT, as I told, it's a generative pre-trained transformer. GPT-1 was the first form of like transformers, and it's a decoder-only platform, decoder-only transformer. What is difference between decoder-only and a normal transformer? Not sure anyone is paying attention. Exactly, right. So normal transformers has 2 parts, encoder plus decoder. But that's what encoder will be there, a decoder part will be there. But GPTs is only decoder only. Okay. Is it okay to remove one part and then only deal with one part? How did it work out? You're removing one part, ignoring that totally, and it still works. How is that? Yes, that is called as tokenization. So in today's world, whenever you heard what is tokenization, it is the encoder part. As part of the GPT, they do not have an encoder. So we need to give the GPTs, because it's only a decoder-only module, we need to give it encoded value. So how to encode the text and give it? There are actually a lot of tokenizers. It's called tokenize. The process is called tokenizer. And the underlying algorithm is called BP, byte pair encoding algorithm. We'll just give an example and try to understand what is a tokenizer further. Again, this will be useful if you're going to try out some training. You will need the tokenizer for sure, based on whatever is the model. So let's go to this one. Right, they do not want to overcomplicate the structure. Already the GPTs that we are talking about is 70 billion, 80 billion, 100 billion, and there is actually even talks of like trillion parameter model. So they don't want it. They wanted to make it very simple and only give it encoded data, encoded values. That is tokenized values. So that was actually the reason. I don't know exactly why it was happened, but that actually helps a lot also. So if you think of like RAG concepts, if you convert it to tokenized or vector data, you'll be able to transform faster. See, encoding, okay, if I go back to the previous statement, encoding also takes some time and decoding also takes some time. Decoding takes the most time because it is doing a generative part also. So they don't want to overcomplicate stuff, maybe separate single responsibilities. I'm not sure. That might be the reason. I'm also not sure what exact reason, but that's a good question. Correct. All GPTs nowadays are only having decoder-only transformers. Correct. But we are actually tokenizing it separately outside. But yeah, you're right. As a model, I don't need to worry about encoding part. I only deal with encoded data. I think that's a single responsibility concept. Yeah. So how to do encoding? That is called tokenizers. I think OpenAI has its own tokenizer. You select a model. Let's take an example. So how does tokenizing work? For example, I'm just giving it a prompt like this. Today's Geeknight is talking about tokenizers. What would be the number of tokens? How it is getting converted? Anyone has any idea? Okay, for each character, it will have token. Okay, that means how many? Well, it is 1, 2, 3. It should have 6 token. That's 9 token. So how it is splitting out is, so it is actually splitting out not on a word piece basis. There are actually tokenizers which actually deals with words. Each word will be 1 token, and there are tokenized. But better than that, if you try something like algorithms like byte pair encoding, they actually try to split the word also. And each of those words, again, for example, token is considered as 1. In the tokenizer, token is considered as one token. For example, here you see 9 tokens. There are 9 tokens. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tokens. So each of those words are split it into separate parts. How it is beneficial is, again, it was actually trained using this kind of tokenizers. Byte pair encoding, you don't need to deal with like entire word. If it's a lengthy word, it will be very difficult. So as a result, there is a process called byte pair encoding. Again, I'm not going to what is byte pair algorithm, byte pair encoding algorithm and all. It's very easy to understand. You can actually give it a try, how it generated that. And so that is something to revenue, like generate revenue for. Uh, there is no maximum. Like I did not get your question. Hmm? Yeah. Need not. Okay. Correct. Because what it is trained on, it is trained on a huge corpus of data, like petabytes or terabytes of data. And in that data, the token word was higher. In a simple words, token word was higher. It will associate token for token word some character. And what it is doing internally is it is converting into some number. So token word it has identified. Token for token word, it is actually going to be 6602. Just taking an example. So if it is going to be 6602, the remaining characters, there will be actually a different token associated for the remaining part of tokenizers. So that is the functionality is actually called byte pair encoding. It's actually splitting words also, and it's actually trying to pair something. They are not taking word as a single token. That is called byte pair encoding. That's an interesting algorithm if you want, and you can check offline. If possible, like we'll discuss later. Okay, so that is the encoding part in all language models. There are actually open source like TikTok tokenizers or this kind of open where you can actually try to get a text and convert it to encoded tokens. Moving on. So far what all we covered, we created like a GPT is a decoder-only model. In order to feed GPT, we need to convert the text prompt into tokens, in basically numbers. And this numbers is what is getting fed into GPTs. Now, all these GPTs are considering having decoder-only model, and what is internally happening. Just talk about this also. So all GPTs usually have something called attention mechanism. Again, these are transformer models. All these are actually having attention mechanism called query, key, and value. Again, these are some weights. You can think of it like some numbers which we get multiplied to whatever is the coming input number. And from those numbers, it'll try to convert it into a different format number, and that will get converted to a what is the decoded value. Okay. So basically what is internally happening is, for example, GPT-3 has a 12 transformer layer. It has 12 transformer layers inside it. So if you wanted to train a already built transformer or GPT, what it takes, what do you need really, what all things do you really need if you wanted to, for example, a GPT was trained with some data that they have already collected the data and then trained it and then created a base pre-trained model. Now, I wanted to train this GPT with my data, new data. For example, it can be financial data, which is created newly, or it can be any kind of data. One use case that I was thinking of is I wanted to train a model based on what are the designs. I've been building some product for last 7 years. All this knowledge, I want to train a model using those data. Now, these pre-trained models will not have that kind of designs or what was built over time, right? So how to train that? So there's a concept called parameter efficient fine tuning. That is why we call it PEFT, or it's fine tuning. So fine tuning, what it is doing is there are 7 billion parameters. For example, 7 billion parameters means there are 7 billion parameters. We can actually try to take some parameters and try to replace it with whatever data we need. That is called fine tuning. So this is, what it is doing is it's actually training, for example, 7 billion parameter. it is taking freezing majority of the parameters. For example, 6.5 billion parameters, it is freezing. The remaining 0.5 billion parameters, it will trying to get the small data sub data set, whatever I want to train, and then it tries to replace the weights such that it is getting trained. The decoder is getting trained on the new data. That is called fine tuning. Everyone clear what is fine tuning? Right. The advantage of this kind of approaches is we are actually not dealing with a huge 7 billion data or 100 billion data. We are only training with very small data like 0.5 billion. These kind of parameters are only we changing. Again, the advantage of this kind of approaches like uses very less resource. You don't need to have a huge compute because we are only dealing with very specific trainable parameters. Okay. And it is actually portable for almost all open source models also, this concept. Again, this concept or fine tuning was actually like initially came up from Microsoft. Microsoft actually, okay, here now. Okay, there's a paper involved how to fine tune a model. Again, this was from Microsoft and it's called LoRA, low rank adaptation technique. So what is LoRA trying to do is, if you have a trainable low rank metrics, if you have a like GPT, like 7 billion parameter model, I am trying to train some portion of it, some parameters with my data, new set of data that I wanted to be trained. Okay, training affects only those metrics with those very specific parameters. And how it is creating parameters is, I'll go to the code directly. That will give you an idea how it is training. In this demo, we will not be able to run because I need huge compute. I will not be able to run in this machine. But what it is doing is, first I'm trying to create a data set, what I wanted to train it on. So once I have the data set, what I'm doing is, first thing, you need to encode the data. Any data set that you want to train it, first part is like tokenize the data. Once you tokenize the data, the next part is you choose a model. What kind of model? I was trying for a very small billion, like 0.6 billion model, Gwen3 model. You train the data set, tokenize it using a tokenizer, and then you apply these configs. Again, these are for doing LoRA. I think the paper actually explains what is these things. Again, these are the LoRA config. LoRA configs means like how much rank I should actually change. The higher the rank means it is actually training more number of parameters. Lower rank means it is only very less number of parameters. Again, this is a cautious decision. How much I should train? I should train with a lot of my data. It can actually do forgetting also. The previous trained data, it will try to forget. So again, this is a trade-off you need to do whenever you want to try to train a model. So one is rank parameter. One is second part is the LoRA alpha. Alpha parameter is actually the learning parameter. For example, it learns a new thing. And if you want to scale it up, the new learning, if you need to give a more weightage, then you can increase the alpha to higher numbers. It will give more weightage to the new learnings. Again, this is a cautious decision. It's called hyperparameter problem. You need to try to train with some combination such that you get a decent output. It should not only learn the new data, it should also have the previous data. Yeah. Mm-hmm. No, there is nothing like that. See, everything is actually trade-off in LLMs. If you want the model to be overfit, these are the parameters that you need to do. But sometimes you need to overfit. You only need to train it on the new data. I'm trying to train it for a specialized functionality. For example, some design discussions or this kind of thing. I don't want it to ask a general question, how is the weather? And I don't want to involve in casual discussions. So even if those parameters are getting lost, it's fine. It's fine with me. I am only interested in new parameter. Then probably this alpha, I can increase it higher. That means it will give more weightage or scaling to the new values, the new train parameters. But again, it's a cautious decision. If you try to overtrain with only the new data, it will not have the capability of an old data, old transformer. You might need to sometimes have like some reasoning model also. If you want to think an answer, then you will also need to think like, okay, I should not overtrain with like huge scale, but very decent. So this is a trade-off. That is a calculation that you need to do. You train it with some parameters, maybe lower value of rank, lower value of alpha, and then see, okay, is it getting a different model or is it a decent enough model? it's a trial and error only. It's nothing like trade-off we can do. It's always there. That clear, right? Correct. See, the higher the number of parameter, it can actually generalize a lot. It can generalize a lot, but the problem is, again, I told back the previous situation, right? For a higher parameter, how much GPU need? If you are thinking of 100 GB, 100 billion parameter, you need a GPU of like, you will not be having one GPU. You might need a set of GPUs, and GPUs are actually very costly. Okay. Quantization is actually, okay, typically every parameter is by default, it's a 32-bit. 32-bit, okay, for folks in Zoom, the question was, how is LoRa different from quantization? So there is a concept called QLoRa, quantized LoRa, but quantization itself is a separate technique. You can actually combine quantization with LoRa. So quantization, what it does is, a typical parameter value, it will be of 32 bits by default. If you don't want 32 bits, 32 bits is still higher. If I go back to the CPU requirement, if I am using a 32-bit, correct. Low rank and Q quantization combined, it's Q LoRa. There is actually distillation. All these are different. I will not go into that much different topic. It will be too much. But what is your question? Is quantization different from LoRa? Yes. All those 4 topics. Okay, quantization will not help train a new model. It is actually existing model only. It is actually just reducing the size. The parameter size is of 32-bit. It can get reduced to 16-bit or 8-bit. And obviously, if you try to quantize into from 32-bit to 8-bit, there is a quantization loss. There are techniques for you to avoid quantization loss. That's a separate topic. It's not dealing with fine tuning. Fine tuning means like you are training with new set of data. And LoRa is actually low rank adaptation is actually an adaptation technique to train new models. There are actually other kinds of adaptation techniques also, but for time constraint, we'll limit it to LoRa. Does that? Okay, going back to the code. So what it is doing is we are giving LoRa configs. These are hyperparameters for the training parameters. And again, this is a trade-off, what you need to do. And again, drop-off is actually, if you wanted to not overlearn it and sometimes drop something, you can actually go for a drop-off value. Again, we give very less values. And what are we targeting in transformers? We are targeting the attention weights. Attention weights means it's either a query or a value. Then there is also one more thing called key. These are the target modules. Again, this is a combination. I only want to target query values of the attention matrices. Then you can only give Q project. Again, this is a combination. You need to trial and out and error. Okay, which one works? You need to go ahead with that. Okay, clear what is LoRa config. Now, once you have that tokenized data set trained, then you can actually go for training arguments. What is training arguments? What it's doing is, in the training arguments, we can actually, if you're using like floating GPUs, you're not having a dedicated GPU for training, then it's better like, okay, after maybe 100 runs, it's better to store that whatever training has been, let's have a checkpoint. So for those kind of things, we can actually give something like save steps. So every 100 steps, it actually tries to train. And this is what, and if you wanted to, you want to resume it from 101 step onwards. In this concept is called checkpoints. This is a good practice if you're going to fine tune something. Yeah. So again, I will not be able to run and show you. It is not workable in my machine, especially when Zoom is running. But any questions on what is LoRa and fine tuning? I'm done with the presentation. Like, that's it I want to share. These are some mechanisms which will help you to train a generic model and fine tune it with your specific data, what you're targeting. Give it a try if you are not tried it out. Again, if you are dealing with resource crunch, you can go for a smaller models like Gwen 3.6 model, 0.6 billion or 1 billion models. The performance will be slightly lower if you are going for higher models like 7 billion parameter model, 8 billion parameter. Those are decent enough models which will give you decent enough results. Yeah, I'm done with the presentation. Any questions, anyone? Try to cover almost in the session itself. But yeah, anyone from Zoom also? There are people in Zoom, they will be on blind. For this fine tuning is actually for pre-training, like based on pre-trained model only. Real time, we will not be able to use fine tuning. After the end results of fine tuning, we'll get a fine tuned model that can be used. But again, if it is going to be frequently changed kind of like for real time data and all, then there are actually alternate techniques like RAG, MCP, or something of that sort, context aware application. These are the things that we know. Fine tuning is not suitable for real time. Some questions in the chat. Let's see. Maybe you can, Yuvraj, you can type your question if you have something. What about QLoRa chase, which LoRa could not? Okay. QLoRa, I think I covered sometime before. QLoRa means it is quantized plus quantization plus LoRa. So it is trying to reduce the size. See, doing fine tuning or LoRa does not increase the size much. You are dealing with very minimal set of parameters. It might increase slightly, but again, it is negligible. If you think in millions and all, it is negligible. We are fine tuning some additional parameters. And we are actually removing also some parameters, but which are low rank ones. But LoRa does not change the parameter size of the model in a nutshell. Quantization is actually effective to bring down the size. If you wanted to, if you're talking about like 7 billion model and it's actually 32-bit parameters, you can actually using quantization, you can actually bring down that size to, for example, 16 GB or 8 GB, which will like half the size of the memory requirements. That is what quantization achieves. Usually fine tuning like quantization plus LoRa is both used and it's called QLoRa. So they said that you already train with new data and it's also a reduced size. So again, but both are two different things. People use it both combined in one shot. Does that answer your question, Yuvraj? Oh. All right. Anyone, any other questions? Speak to that mic. Okay, so hyperparameters is what you need to try out. Okay, you are talking about 7 billion parameter model or 100 billion. Okay, so it depends on what kind of data set you're trying. You are trying to train very small specific data set. Probably a decent 7 to 8 billion is the right fit. In all this, there is no like right thing. All these are trial and error. So I try to train my organization knowledge with a 1 billion parameter model. It gave all the wrong answers. It did not train anything. I tried to change the parameters over the time. There were some improvements, but again, eventually I had to change the model itself. Instead of 1 billion parameter model, to change it to 7 billion parameter model, which was giving decent enough results. It's all trial and error. That is what I can tell. There is no fixed rule. Depends on the situation.
In your experience, have you tried RAG before fine tuning, and how was it in comparison?
Actually, RAG works better. RAG, we were able to achieve it in very short span. RAG is easy to implement. But yeah, so why we went with fine tuning is I wanted to like quantize it and make it very small, and wanted that model to run as part of every machine, every developer machine. So that kind of use case RAG will not do work. Like the objective of my intention or the project was different. But RAG works. I already tried with RAG. RAG actually works seamlessly.
Okay, thanks.
Does that help? So ChatGPT does the encoding and then submit to transformer. If so, what is the embedding model it uses for any GPT variant? But what is the advantage we gain through this? Instead, we can have even encoder to write. Yeah, I think that question was asked. Why did we remove encoder from transformers and then try to build GPT as a decoder only model? I do not have an answer for that. My reasoning for that would be like they wanted to separate something separate loud. And again, they don't want to make it like hard and fast rule. Only the encoder of this transformer. They might have to generalize it. Maybe that is my rationale. I'm also not sure. Same question was asked here, so I'm just repeating. Does that help? Need to go for agentic RAG instead of RAG. It was not about RAG. Okay, but I do not have an answer. I usually have not used agentic RAG. I used RAG, very small RAG function, but I do not have the answer for that. And the topic is not for RAG based. Okay. Anyone, any other questions? All right, then. Thanks for your time. Yeah, you can take over.
So thank you, Deepak, for your wonderful session, and thanks to all the participants for joining with us in person and both with Zoom. So please take a minute to share the share your feedbacks. We'd love to hear from you. Like please scan the QR code and give the feedback. So the people also in Zoom, please give your feedbacks. And then we also invite you for the next sessions of Geek Nights from upcoming months. So with the new set of themes. So uh, like of course like Geek Night is not without complete with snacks. So you have your refreshments in pantry. So please collect your refreshments and get connect with each other. Thank you guys. Thank you.